Alright, hello again everyone. This is Ivan from Brainy-Bits.com. Today I'm going to show you how to control a DC motor using a motor driver. This one is the L9110S dual motor driver. We're only going to connect one today, but you can connect another one here on this terminal to connect another one. And the way we're going to control the speed and direction of our motor, we're going to use a rotary encoder. Basically a rotary encoder keeps on turning, there's no end to it, in one way or the other. So we're going to control the speed and direction with this. And also there's a switch that's integrated in it. And we're going to use that to actually put the value at zeros, meaning stop the motor. So we're going to go through the connections. And after that, we're going to go see the code. We're going to use an interrupt today to actually read the value of the rotary encoder. Because if we weren't using an interrupt, it would be hard for our code to do anything else but look at this to see if anything is changing on the rotary encoder and do anything else. So it would be bogged down by looking at this. By using an interrupt, when this happens, when it detects that something is happening on the rotary encoder, it will stop the code, read the value, come back. So we'll look at that later. Connections are pretty simple. On a rotary encoder, we have a clock, a direction, a switch, and voltage and ground. Now our clock is connected to pin number 2. This one is important that it's connected to number 2 because this is the one that we're going to use for the interrupt. On a Uno, we have 2 available pins for interrupts. We have pin number 2, which is interrupt 0, and pin number 3, which is interrupt 1. Other Arduinos have more or less, well, more, I guess, interrupt pins available, but on the Uno we have 2. The other pins, number 3 is connected to our direction, and number 4 is connected to our switch. Voltage and ground is connected directly to the Uno because this uses almost no power. So that's for the encoder. The motor driver, we're using a breadboard power supply to supply 5 volts to the breadboard rails because we don't want to drive a motor directly from the Uno. Motor tends to draw a lot of current. Even a small one like this could, well, maybe not damage, but at least reset the Uno. So, yeah, so we're connecting voltage and ground to the breadboard. And the other 2 pins, B1A, B1B, one is for the pulse width modulation signal, and the other one would be for direction of the motor, pin number 10 and 11. As always, you can go to our website, Brainy-Bits.com. You'll find a tutorial there, and also you'll find a schematic which will show you all these connections a lot better, so you could go and check that out later. After that, our motor is connected to our module. These you can inverse. There's no really a polarity here. What will happen basically is the motor will spin one way or the other depending on these connections. One thing to note though, the motor needs to have a little capacitor like this between its terminal. This is to prevent spikes or sparks to actually reset our Arduino. So this is a little 1 UF capacitor. Most of the time these come soldered onto the motor itself. If not, just add one of those and you'll be fine. So this is the connections we need to make. We're gonna go see the code. The code is a little bit long, but most of the code, what it does is check the value of this to set the speed and direction of this. So basically it looks long, but it's not that bad. And we'll look at the interrupt also in our code. So let's go take a look at that. All right, so here we are at the code. This is the code we're going to use. Now, like I said, it looks long, but mostly all this part here, all it does is check the rotation of the, it takes the rotation value of the rotary encoder and translates that into a direction and a speed. So all this stuff, that's all it does. So we're going to start at the top here. We're going to define 2 variables, turn detected and up. And we're going to put those volatiles because we're going to use these in the interrupt code. So they need to be volatile for interrupts. Then we do our pins and the connection to the motor driver. And then we define motor B PWM for the PWM speed to that connection here, and this one to the other connection. Then this is the interrupt. So basically This will run if the CLK pin on the encoder goes from high to low. Because when you turn a rotary encoder, it goes from high to low, meaning something has happened. So if something happens, it's going to run this little bit of code here. At the beginning, we put a delay of 4. That's for debouncing the rotary encoder, so we don't skip or repeat steps. Then we do a digital read. If it goes clockwise, then we set up to that value. Else, it's going counterclockwise, so we do the not to actually put the opposite value. And then we put turn detected to true, meaning a turn has occurred on the rotary encoder. Then we're at our setup, so we set our inputs. And then we put the SW, which is a switch, to high to enable the pull-up resistor for the switch. Then we attach the interrupt, 0 because we're using pin 2, the ISR, and falling, meaning going from high to low. Pin for the motors at output, and we put them both to low to set the motor to off at the beginning. Then we're going to do the loop, our main loop. So static long rotary position equals 0. That will be the value of the rotary encoder. We set it to 0, so at the beginning it starts at 0. It's a static, so it counts correctly the steps. Now we check if the button is pressed. If it is, and the rotary position is already equals 0, then we don't want to do this bit of code here. So if it's already at 0, it means we already ran this, so we're going to get out. If it's not at 0, we put it at 0, and we put both pin of the motor to low to turn the motor off. And then we print reset in the serial monitor window. And the position also, which would be 0. Now, this will run if rotation was detected. So if turn detected, so in our interrupt up here, where is it? There it is. If there is a turn, then we said turn detected equal true. So we're going to go here. Turn detected, yes. If it's up, meaning clockwise, we're going to check the position. If it's greater or equal to 100, then we're going to set it to 100 because we don't want to go higher than 100. If it's not, we're going to increase its value by 2. So if it's, let's say it's 52, it's going to go to 54. Else, meaning it's going counterclockwise, then we check if it's smaller or equal to minus 100. If it is, we set it to minus 100. We don't want to go higher than that. Else, it does the same thing. And then we do turn detected to false. So it waits until a new rotation is detected. We are going to print the speed, meaning the rotary position that it's at. Now the rest of the code is basically all it does. It takes that rotation position value and sets the motor to a certain speed. Rotary position is greater than 0 and smaller than 11, meaning between 0 and 11, then we don't do anything. We don't want to turn the motor at that point. If it's greater than 10 and smaller than 21, then we say digital write high. That means the direction is forward, and a power PWM of 180, which is fairly low. It goes opposite. The smaller the number, the faster the speed, and when you go in reverse, it's the other way around. So we do these until we get to 100 right here. If the rotary position is greater than 90, then the value is going to be 20, which is full speed or maximum speed we could go. Now we do the same thing for the counterclockwise, but we're using negative values. So if rotary position smaller than 0 and greater than minus 11, then turn power off. We don't want to do anything at the beginning. Same thing for between minus 10 and minus 20. But as you can see, the values are opposite. Instead of being 180 for slow, now it's 40, so we're going the other way. And all the way up to 200, which is full reverse speed. So there you go. You know, it's not too complicated. You just got to take it one line at a time, and it's, you know, you'll get it. It's the interrupt is not too hard to understand on this one. One thing I did notice, the delay of 4 is important for debouncing, and it works fairly well. So it's a simple way to do the debouncing of the rotary encoder. So we're going to compile the code, upload it to the Uno, and check it in action. So let's take a look. All right, so we're back. We already uploaded the code to the Uno. We powered up the breadboard to give power to our module and plugged it in the Uno, so it's ready to go. Nothing's happening right now because I haven't turned my rotary encoder yet. So I'm going to go ahead and go clockwise first, and you'll see the values changing on the serial monitor at the same time. So here we go. So there we go, our motor starts. We're at 12, so once it hits 10, it starts going a little bit faster as we turn, all the way to 100. And there we go, full speed. I can bring it down, or I can just press the switch to stop it completely. There we go. Now we're going to go the other way in reverse. Same thing. As I turn it, increases up to 100, and then it stops there. Going back down and pressing the switch to stop. So there you go. That seems to work pretty good. Our delay of 4 that we put to debounce the rotary encoder seems to be working pretty good. We're not jumping too much and not missing any steps. So there you go, guys. That's one way to control the speed of a motor using a rotary encoder. And to drive the motor, we're using the L9110S. As always, look at our website. You'll find the schematics, the code that we use to make your life a little bit easier instead of retyping everything. And also, you know, that's one way to do it, but go ahead, modify the code, play around with it. That's how you learn. Once again, I'm Ivan from Brainy-Bits.com, and I hope to catch you guys later.